Good morning, children. This is 12th Physics. We are doing chapter number 9, Ray Optics. Today we are going to start with a topic that is refraction at convex surface. Now, your children, this surface is the refracting surface. So as we see, the shape of this surface is convex. So this topic is refraction at convex surface. Now, this is a boundary, this is the interface between two media. Here the media is air and refractive index of air is 1, and here the media is having the refractive index mu. So air is the rarer medium and mu is the denser medium. So here children, light is going to get refracted from a rarer medium, that is air, to a denser medium having refractive index mu. Now here children, P point is the pole, right? And C is the center of curvature of the convex surface, right? And this PC will be, the distance PC will be the radius of the curvature, right children? Now, here we are supposing a point object O. Here we are supposing a point object O. So let's draw an incident ray starting from point O. So this is the incident ray, the red color, and the black color is the normal. So this dotted line which is passing through the center of curvature is the normal at point A. So the angle between the incident ray and the normal, that is this angle, is your angle of incidence I. Right? Now as the ray of light OA is going to enter from rarer medium to denser medium, it will suffer refraction. And if the second medium was not there children, then the light would have gone straight like this, right? But as the second medium is having the refractive index lower, the light is going to bend towards the normal. So the light bends towards the normal, and this is your refracted, the green color is your refracted ray. The angle between the black normal and the green refracted ray is known as the angle of refraction, which is denoted by angle R. Now, here we have named some angles. So now children, as we know, our object is at point O. So all the distances we know they are measured from the pole, right? So the distance that is PO is the object distance, and we know according to the sign conventions, PO is on the left hand side, so it will be taken as negative. So PO is equals to minus U, that is your object distance. Now here children, PC, as we know, it is the radius of curvature, it is on the right side, it is along the incident ray, so it will be taken to be as positive, so it is plus R. Now the distance, the image is formed at I. So the distance Pi is the image distance, and as it is along the incident ray, as it is on the right hand side, it will be taken to be as positive. So Pi is equals to V. This is all about lengths. Now let's talk about some angles. We have already talked about the incident angle and the angle of refraction. So these are the angles between the normal, the black color normal, and the red color incident ray, that is angle of incidence, and the green color refracted ray and black color normal is angle of refraction. Here we have named few more angles. So this is your angle alpha, Here we are having angle beta, and here we are having angle gamma. So children, gamma we have written something like this. Just a minute, let me change the color. Gamma we are writing something like this with a curl, right? Curl like this. This means gamma. So this is your gamma, right? R we have written simply like this. Okay. Now, children, we know now that according to Snell's law, that sin I by sin R, the ratio of sin I by sin R is a constant, that is the refractive index mu. So mu equals to sin I by sin R. This is according to the Snell's law. Now we know, children, when the angle I and angle R are very small, for that we can write, if the angle I is very small, then we can write sin I to be nearly equal to angle I. Similarly, here we are telling that angle I and angle R, they are very small. So as they are very small, sin I is nearly equal to I and sin R will be nearly equals to R. So instead of sin I by sin R, we have put I upon R. Right, children? Now, if we make I subject of formula, I will be equal to R will go in multiplication with mu, and you are going to have I equals to mu into R. Right? Now, children, we are going to write these in terms of the other angles, that is alpha, beta, and gamma. Okay. So, let's write that. So, children, here I, we know that angle can be written as arc upon radius. Angle is arc upon radius. Yes, children. So, if we want to substitute the value of angle I, this is one thing you have to remember, right? Let us consider this triangle. That is triangle OAC. Here we are having a property in maths that the exterior angle, that is I is the exterior angle to triangle AOC, right? The exterior angle is equal to the sum of opposite interior angles. So for this triangle, that is triangle OAC, I is exterior angle and opposite interior angles are alpha and gamma. So I is equals to alpha plus gamma. So instead of I, children, we are substituting alpha plus gamma, right? Mu will be as it is. Now let's substitute the value of R using the same property. Now we are going to consider the triangle, and that triangle is this. The triangle name is triangle ACI. Triangle ACI, right, children? Now this triangle, this is gamma, right, beta? This is gamma. Gamma is the exterior angle and R and beta are the interior angles. So can we write gamma exterior angle is equal to the sum of opposite interior angles. So interior angles, gamma we are writing like this, and this is R plus beta. Right, beta? If I make R subject of formula, then R equals to gamma minus beta. Yes, beta? So here we have written gamma minus beta. So here we have used the property of maths, that is the exterior angle of a triangle is equal to the sum of interior opposite angles of that triangle, right? Now, for this equation, let's substitute the value of these angles. So we are going to use this definition that angle is equal to arc upon radius. Now let's talk about angle gamma. Let's talk about angle gamma. So if you look this area, right? Here this is gamma. So which arc do we have in front of gamma? It is arc AP. Radius is PC. So gamma angle gamma can be written as AP upon PC, that is arc upon radius. Let's substitute the value similarly of alpha. Let's substitute the value of alpha, right? So here, if we consider this part, sorry, for alpha, we are going to consider, children, here is alpha, right? So alpha, in front of alpha, what arc? We are having same arc, that is AP, and radius is, children, PO. So it is AP by PO. Now let's substitute the value of gamma. Gamma we have found out, it is AP by P, it is AP by PC, that we have done, right? Now let's substitute the value of beta. Beta, let's consider this part, right? This is beta. So beta equals to arc. What is arc? Arc is AP. And what is the radius? Radius is PI. So it is AP upon PI. So we have substituted the angles by using the formula angle equals to arc upon radius. Now children, if you see carefully, on left hand side and on the right hand side, we are having AP. So if we take AP common, AP will finally get cancelled. So our equation will become, as AP gets cancelled, our equation becomes 1 upon PC plus 1 upon PO equals to mu bracket 1 by PC minus 1 by PI. Now children, let's substitute the value of PC, PO and PI. PC is what? R. So we are going to substitute the value of PC, PO and PI from here. So PC is R, so it is 1 upon R. PO value is minus U, so plus 1 upon minus U equals to mu. PC is again 1 upon R minus PI is V, 1 upon V. Right? Now we are going to multiply mu inside. On multiplying mu inside, we will get this equation, that is mu by R minus mu by V. Now we are going to take the terms having R on both the sides on one side. So here we have rearranging the terms, we will get this, that is 1 upon R, we are sending that side, so it will be mu upon R minus 1 upon R, and this mu upon V will come this side, it will become positive, that is mu upon V minus 1 by U. If we take R common, if we children take R common, it will be mu minus 1 by R, which is equal to mu by V minus 1 by U. Right? Now children, here we had considered that the first medium is air and its refractive index is 1. But suppose you have given some medium with the refractive index mu1 and mu2. Then children, no need to worry. You are just going to substitute the value in the last step. That is, you can write mu equals to mu2 by mu1. So just substitute this value of mu in this equation and you will get this equation, and in this equation you can see that you are having the refractive index of both the mediums, that is mu1 and mu2. Okay, so children, this is your refraction at convex surface. Now let's talk about refraction at concave surface. Let's try to understand the diagram first, beta. Now children, here as we see that the refracting surface or the interface between the two media, is of concave nature, concave shape. So the topic has been named as refraction at concave surface. Let's try to understand the ray diagram. Now what happens over here is P is the pole and C is the center of curvature. Right children, the distance from P to C is the radius of curvature, and as it is on the left hand side, we will denote it by minus R. Now, here again the medium on the left hand side, medium 1 is air and medium of the concave surface is having the refractive index mu. Right? Now, let's try to understand the rays. Right? So here children, you have supposed an point object, that is O. Point object, that is O. So if we draw an incident ray like this at point A, the angle of incidence, that is the angle between the incident ray and the refracted ray. So this is your black color is your normal, because we know that the line passing through the center of curvature is your normal. So the angle between the red color incident ray and the black color normal is your angle of incidence, that is I. Right, children? Now, if there was no second medium, the ray would have gone straight like this. But as there is a second medium, the ray will not go straight like this. Okay, so what happens as the ray of light is going to enter from a rarer medium to a denser medium, it suffers refraction, right? So it is going to bend towards the normal. So instead of going straight, the ray O is going to bend towards the normal and the ray will come like this. That is, green color is your refracted ray. Right, children? Now, if we extend the refracted ray back, it will appear to be coming from point I. So I is, and for the image formation we require two lines, right? And one ray we are drawing, that is along the principal axis, and that incident ray is this, and it will pass undeviated. It is going to go straight. Now the two incident rays, the red color incident rays, they are never going to meet, so we will extend them backwards, right? The green color refracted ray, let me change my words. This is your oh god, what happened? So children, here this is your red color, and this is our refract. Now the two green refracted rays, they are never going to meet each other. So what we will do, we will extend them backwards. So on extending them backwards, they appear to meet at point I. So for the point object O, the image is formed at I. Right, children? So this is your explanation of the ray diagram. Now your angle I is clear, angle R is clear. Angle R is the angle between the refracted ray and the black color, that was your normal. That angle is angle R, right, beta? Now here we have named some angle. This is alpha angle, this is your beta angle, and again this is your gamma angle. Right? Now children, we need to use some geometry over here. What we are going to do is, as we had used previously, the same thing the same concept we are going to apply over here also. So children, let's consider the triangle, and that triangle is OA. That triangle is OAC. Now in triangle OAC, gamma is the exterior angle. So exterior angle is equal to, let's see which are the opposite interior angles. So if we see alpha and angle of incidence, they are the interior opposite angles. So our gamma will be equal to alpha plus I, right? This is one thing. Now let's apply this again to one more triangle, and that triangle is AIC, and that triangle is AIC. Here let me tell you one thing. Here children, this angle, that is angle IAC, is angle R, because they are going to form vertically opposite angles. So here, as the angle is R, here also the angle will be R. So in this triangle, that is triangle IAC, in triangle IAC, gamma is again the exterior angle, and the interior angles are beta and angle R. So gamma equals to beta plus R. Okay, beta plus R. This much is clear. Let's move forward. Now we know PC is the radius of curvature, which is on the left hand side, or which is in the opposite direction to the incident ray, and so it is negative. Next, PI. PI is the image distance, which will be denoted by minus V, and PO is the object distance, which also will be denoted by minus and U. Right? Now again the same concept we are going to use over here, that as angle I and angle R are very, very small. They are very small. So as they are very small, sine of I will be nearly equal to I, and sine of R will be nearly equal to R. So mu equals to sin I by sin r can be replaced as mu equals to I by r. Mu equals to I by r, right? And if we make I subject of formula, r will go in multiplication with r with mu, and the equation will become I equals to mu r, right, children? Now let's substitute the value of I from the equation over here. I can be written as gamma minus beta, so it is gamma minus beta. R can be taken from this equation, and that is gamma r. If you make subject of formula, this is r, so r will be equal to beta will go that side, that is gamma minus beta, right? We have substituted the known angles. Now instead of angles, what we are going to substitute? Angle is equal to arc upon radius. Angle equal to arc upon radius, right, children? So instead of I, so we are going to consider this AIP. We are going to consider AIP. So for this is for beta, right? This is for beta. For beta, it will be arc AP and radius is, children, PI. So for beta, we have substituted AP upon PI. Yes? Now, let's substitute for gamma. Let's substitute for gamma. So for gamma, we are going to consider this part, that is A, C and P. So for gamma, if we see the arc is beta AP and the radius is PC. So let's see for gamma, AC, AP by PC. For gamma, it is AP by PC, right? Now what's left? Alpha. Let's substitute the value for alpha. Alpha, we are going to consider the bigger triangle, and alpha, the arc opposite to alpha is AP and the radius is PO. So alpha is AP by PO. This much clear? Chalo. Now you can see that AP is on both the sides, so AP will get cancelled. And as AP gets cancelled, we are left with 1 upon PC minus 1 upon PO, which is equal to mu 1 upon PC minus 1 upon PI, right? Now we know the value of PC. PC is minus R. So we have substituted instead of PC minus R. PO is minus U. We have put instead of PO minus U. Again PC minus R, and PI value is minus V. We have put it minus P. Now multiplying mu inside and rearranging the terms, you are going to get, and taking r common, you are going to get mu minus 1 by r equals to mu by v minus 1 by u. But if in derivation they ask you to derive the diffraction at concave surface for two media, one having refractive index mu1 and other with refractive index mu2, simply you can substitute the final equation, that is mu equals to mu2 by mu1, and this is your resultant equation. So this was refraction at concave surface. Now let's move to lens. So children, we all know lens is a transparent material which is bounded by two surfaces, and either both the surfaces are spherical or one of them is spherical. Now we know that the lens are of two types. First we have a concave lens and other is convex lens. Now let's talk about convex lens. Convex lens, we are very well aware of the shape. This is the shape, that is in middle it is thick and in the edges it is thin. That is, it is also known as converging lens because it converges light at a point after refraction, right? Concave lens. Concave lens, their middle part is thin and their edges are thick, and they are also known as diverging lens because the light that is incident on that, this is the incident ray, right? It diverges it like this. So it is also known as diverging lens. That is your concave lens. Now children, convex lens, they are of various types depending upon the nature, depending upon the two surfaces. Now here if we see, both the surfaces, they are convex. So as both the surfaces are convex, it is known as double convex lens, which we simply call it as convex lens. Now here in this type of lens, the one part is plane, another part is of convex nature. So it is known as plane convex, so it is plano convex lens. Here if we see, children, this part is convex and this is your concave part. So it is a combination of concave and convex. So it is a concavo-convex lens. So these are the types of convex lenses. Now let's move to the types of concave lenses. So here again, children, the first lens here, this side is concave, this side is concave. So this is your double concave lens, which in simple terms we call it as concave lens. Next one, if you see children, here one side is your convex and other side is concave. So this is a convexo-concave lens. In the third one, this is plane side and this is a concave part. So this is your plano-concave lens. So these are the types of concave lenses. Now children, let's talk about some of the terms that are used in the lenses. Right. Let's start with the first term, that is the principal axis. So principal axis, it is an imaginary line. Principal axis is an imaginary line which is an imaginary straight line which passes through the center of curvature of both the surfaces of the lens. So as it has two surfaces, there we have two center of curvature, and this is a straight line, imaginary line, which is passing through the center of curvature of the two surfaces. Right. Next, let's talk about the optical center, and that optical center is beta R point O. That is over here. O here and O here. So children, this is what? This is your point which is lying on the principal axis, right? And through this point, if the ray of light passes, it does not suffer any deviation. It is going to pass undeviated without any lateral displacement. So if the light is incident at the optical center, it will pass straight without any deviation. So that is your point which is lying on the principal axis. Right. Next, let's move to the next part, and that is your principal focus. Principal focus. So for principal focus, suppose this is your convex lens. This is our principal axis. This is the center of optical center. Right, beta? This is your optical center O. Optical center O, and this is your center of curvature, that is C2, and here also your center of curvature C1. Now children, those rays of light which travel parallel to principal axis, they are going to, as this is your convex lens, converging lens, after refraction they are going to converge at a point on the principal axis. This point on the principal axis where the incident rays of light, which incident rays, which are parallel to principal axis, after refraction they converge, they actually meet at this point, which is again on principal axis. This point is called the principal focus, that is F. Principal focus, that is F. Right. In convex lens it actually meets, and let's talk about in concave lens. It is like this. This is a principal axis, this is the optical center, this is center of curvature C2, center of curvature C1. Now let's draw the incident rays. This is incident ray number 1, take it till here, and this is incident ray number 2, and let's draw the refracted ray, and as we know it is a diverging lens. Here children, diversion of the ray will take place like this. Now if you see the green color refracted rays, they are never going to meet each other. Now if the two refracted rays does not meet, then where will be the image form? So If we extend them backwards, then it will appear that they are meeting at a point on principal axis. This point on principal axis where the refracted rays, they appear to meet, right? That is your principal focus for your concave lens. So let me define the term once again. When the incident rays, which incident rays? Which are parallel to principal axis, after refraction, they actually meet or they appear to meet, right? They appear actually meet or they appear to meet at a point on principal axis, and this point is known as the principal focus F. Now the distance between the optical center and F is known as the focal length, and which is denoted by small f. The focal length is the distance between the optical center and the principal focus, right? Now, the last term in this is aperture. Aperture, children, it is the diameter the of the area of the lens from where the light is getting refracted. So the diameter of the lens is known as the aperture. So this part, right, that is your aperture. Let's move to the rules which we are going to use for the image formation. The first rule for the convex lens is if the incident ray is parallel to principal axis, we know, then after refraction it will pass through principal focus, right? And the rule number 3 is just reverse of this. That is, if the incident ray is passing through focus, then after refraction it will become parallel, right beta? Rule number 2 is, we know, if the incident ray passes through optical center, then it will go straight, it will pass undeviated, it will not suffer any deviation. These are the 3 rules. The rules are same for convex and concave. Again, here the first rule is if the incident ray is parallel to principal axis, after refraction it will, sorry, just a second, this is for convex only. So okay, these are the ray diagrams, beta. Now let us do them one by one. Let's talk about the first ray diagram. Here the object is at infinity, right? So the rays that are coming from an object which are at infinity are parallel to each other. And we know, children, that the rays which are parallel to each other, after refraction, they meet at a point, and the point is F1. So object which is at infinity, its image is formed at a point, and that point is your on principal axis, and that point is the principal focus, and here it is shown by F2, right beta? The image is formed at F2, and we know, children, that the image that is formed at F2 is point size. It is highly diminished, and the image formed is due to the actual intersection of the rays. The image is real, inverted, and it is formed at F2. Next, position of the object. Now we are bringing the object near. We are bringing the object beyond 2F. So here we are going to draw two incident rays. One ray is parallel to principal axis. So after refraction, it will pass through focus. Second ray we are drawing from the top of the object, that is from A through the optical center. It will pass undeviated and they intersect each other at this point. And so this point is the image of our starting point. Our starting point was A. So this is the image of A, and that is known as, we have denoted by A dash and B dash. So the image of the object AB is formed at A dash B dash. So if we talk about the size, then the size of the object is smaller. It is real because the image is formed due to actual intersection of the rays. It is real, and if it is real, it has to be inverted, and the image is formed between F2 and 2F2. So the image has moved far. Here the image was formed at F2. Now the image has shifted. That is, it is between F2 and 2F2. Right, beta? Now let's bring the object more nearer. That is, it was beyond 2f1. Now we are bringing the object at f2f1. So when the object is at 2f1, we are going to draw one incident ray which is parallel to principal axis. So after refraction, it will pass through principal focus. And second ray we are going to pass from the optical center, which will pass straight. So the image is formed at 2f2, right? Here the image size and the object size are equal and the image is real and inverted. Let's talk about the fourth case. Now we are bringing the object between 2f1 and f1. So here the image, as you can see, it is formed beyond 2f2. Again, we are used the same rules, right beta? The image size is bigger, it is real and inverted. Okay. Now let's move towards the fifth case. That is, the object is at principal focus F. So one ray parallel to principal axis passing through focus, other ray through O. Now if you extend them, they are going to meet somewhere at the infinity. So when the object is at principal focus, the image formed is highly enlarged, right? And actually the rays will intersect, so it is real and inverted, and it is formed at infinity. Now, here this is one special case, and this is the only case where the image that is formed is virtual. The image formed is virtual. So let's see this case. Now the object has shifted from principal focus. It has come between the principal focus and the optical center O. So here you will see this is the ray parallel to principal axis. After refraction, it is passing through focus. Second ray we are drawing through optical center O. Now they are not going to meet each other if you even extend them. So we are extending them backwards and they appear to meet somewhere back, and the image of the object, that is this small ab, is formed a dash b dash. So the image formed is virtual, and as it is virtual, it is erect. The image is formed on the same side of the lens where you have placed the object, and the image is enlarged. The image is enlarged, right? Now let's talk about the ray diagrams for the concave lens. Concave lens, children, you are having only two cases. First is the object is at infinity. So we know when the object is at infinity, the rays, we are going to consider two parallel rays and our image will be formed. So two parallel rays to principal axis, we know they are going to get diverged. They are going to get diverged. Now, they will get diverged in such a way that you extend them backwards, they are going to meet that focus. This is our rule, right? If the incident ray is parallel to principal axis, after refraction, it appears to pass for your concave lens. So, our object is at infinity, its image is formed at f1, and image is point size, and it's virtual and erect. Now, object is somewhere between infinity and optical center. It can be anywhere, right? The image formed will be the same. That is, this is your, this is your object, and this is the image formed due to that. Okay, children. So this is it. This was about the lens. We saw about the lens, the types of lens, the important terms related to lens, and we saw the image formation in the lens. So this is it for today. We'll continue tomorrow. Thank you, children.